Here is a question from multivariable calculus. It involves the chain rule. So we've got functions here that are kind of functions of functions. And the chain rule is I've got to say, the chain rule is pretty easy to apply. All right? For me, I can never remember the chain rule, but I can always derive it very quickly. Okay? So it's up to you. Here we have u depends on two things, x and y, and x and y depend on two things as well. So think of x and y as kind of intermediate variables, because ultimately x depends on two things, s and t, and y depends on two things, s and t. So you can think of u really, ultimately, as a function of s and t. Okay? Now, if we want to find this partial derivative du dt, how do we do it? Well, we're going to use a chain rule, but I can never remember the chain rule, so I always like to draw a little diagram, right? And what the diagram shows is the dependency or the relationship between the variables. Let me show you what I mean. We see that u depends on two things, x and y. So what I do is I draw a u and then I draw a little branch or a split to denote that u depends on x and y, intermediate variables if you like. And then I look over here and I say, haha, x depends on two variables, s and t, and y depends on two variables, s and t. So I can make some further branching and come up with this little sort of tree diagram or something like that. Now, how do you use it? Well, I'm glad you asked. Suppose you wanted to calculate du dt. What you do is you start at the u and you find all the paths down to a t. When you go from letter to letter, you form a derivative. Okay, let me say that again. You want to find all the paths to a t from the top to the bottom. And then when you go from letter to letter, you form a derivative. So there's two t's down here, so there's two paths. So I start up here. So du dx times dx dt, plus the other branch, du dy times dy dt. When you go from letter to letter, you form a derivative. That's it. Okay? So the good thing about this model is that it's scalable. Right? If you had 100 variables in one function and each depending on another 100 variables, it's easy. Well, it's not easy, but you'd have a chance at least drawing a diagram. Okay, so this is the chain rule diagram. So by the chain rule, we have the following. Du dt, right, du dx times dx dt. Plus the other branch, du dy times dy dt. Okay, so all you've got to do is compute those derivatives now, and you are good to go. So what's du dx going to be? Let's go up here. Differentiate with respect to x. You hold y constant. You differentiate with respect to x. Well, again, you can use a chain rule there if you want to, but it's probably not necessary. Okay? If you're really struggling to compute that derivative, write the square root as a power to the half. Okay, and then you can bring the half to the front, bring the 2x to the half, 2x to the front, and decrease the power of half by 1. All right, dx dt, that's my relationship between x and t and s. So imagine s is a constant and differentiate with respect to t. So I'm going to get something like that. du dy, well, it's going to be almost the same as here, except we're going to have a y here. dy dt, well, imagine s is a constant, differentiate with respect to t. So cosine t is going to go to negative sine t. And there you have it. Now, it's a bit of a mess. It's a bit of a mess, because you've got x's, y's, s's, and t's in there. Which variable should you have? Well, if you're computing the derivative with respect to t, I would expect that you probably transform this into t t's and s's. Maybe it's not necessary, but that's what I'm going to do. Okay, so I'm going to replace x with that, y with that, and then just simplify. Okay, so the 2's will cancel off. So I'll have e to the st up there times st. So I'll get that over the following. All of that squared. Okay, plus the halves will cancel, y will go to that. Okay, let's I can fix that up in a minute. Oops, sorry. That's just plain old cos t in there. Okay, the square's up there. Right, if I wanted to put it all in under one sort of common denominator, I'm going to get this. Done. So a good exercise now would be for you to calculate du ds.